Yeah, so I'm a master's degree student in academia track at Aalto University. And currently I'm working as a data scientist and machine learning engineer in Plan Brothers. And previously I worked as a full stack developer for 5 years. So I have this background of both engineering and now I'm transitioning into data science. So yeah, the research project was done at Plan Brothers, which is a Finnish startup, and it has these two nice products which are being used all over the world. And we do have office in Finland, and then in South America. I think there was also some office in UK, but majority of the product has been used through some let's say, big organization all over the world. So the product itself is auditing tool and incident reporting tool. So if you are a big organization, let's say store, a big chain store, or if you are some facility manager or even a municipality, then there might be some regulations, or just to improve your own service, you would need to conduct this kind of audits. So the audit might be maybe not financial audit, but just like an audit of a premise. Let's say if you own escalators, you would need to check like every week how the escalators work. So traditionally this is done by pen and paper. Somebody's having checklists and they have to do it in pen and paper. They have to transition this data into Excel and so forth. But we kind of made this system to work flawlessly with the help of just mobile device. And the other tool is incident reporting tool, where if a user sees some kind of like something is broken, something needs to be fixed, they can report different type of observations or insights, and that goes to the right authority, which then take care of that problem. So the tools are being used even by municipalities, by cities, by big organizations, and even small organizations all over the world. So the fact is that Plan Brothers have brilliant engineers which have really good experience in both front-end and back-end development, as well as database and database architecture and design. But so far, there hasn't been this like machine learning project which could be integrated with the tools. So with this project, Plan Brothers wanted to know what are the machine learning systems, how can they integrate within our systems, and what are this more or less software engineering term technical depths that you can have within these systems, and if possible to demonstrate some peculiar attributes of machine learning, for example, some characteristic you would like to take into account when you build machine learning system. And at the very end, as a proof of concept, to build this sales forecast tool, which will basically just forecast the income or profit of Plan Brothers. So, so let's get started. Let's start with the theory about machine learning systems in practice. There has been pretty good research paper, and one of them is by some engineers at Google, which were first demonstrating that machine learning system actually has a huge burden behind. So some things that we'll be talking like, it has been so ubiquitous. I mean, it's so easy to use machine learning models to build them and maybe even deploy. So it's kind of like cheap and fast, considering the fact that there are so many open source tools and even like ready-made tools available. So there is this misconception that it's fast and cheap to kind of like integrate a machine learning model within your project. So what usually is not taken into consideration is that these systems, they actually require a lot of infrastructures around them. And this infrastructure includes data, deployment, and machine learning pipelines. So the data pipelines itself, it takes care of some, let's say, data funneling, some training, deployment, and monitoring. The data funneling, for example, in, let's say, traditional software development, your data basically maybe comes from one source. You you have more or less full control over your data. You can even change your data structure. You can build forums and manipulate what exactly data is the user inputting. So you have basically full control of the input that user puts into your system. And then you can build, let's say, different types of validator tests and so forth to ensure that the data is exactly the way you want. These things do not work exactly in machine learning system because your data could come from different sources. And most of the time, you don't even have this control over your data. Because imagine like if you're building some forecasting model that is based on your sales data plus some data that is coming from the application, let's say application usage. Or if you are in the gaming industry, you would like to see like how many hours is the guy playing and how much money he has spent on some gadgets or so forth. So your data, you don't really have control over the data sources, but you can still run some kind of like transformation. So that's one thing you have to consider, that the data funneling is important. Then the training is also, it needs an environment of its own. Let's say if you are working one person, it might not be the biggest issue, but if you are a team of data scientists, then you would like to have this environment which can be reproducible. Deployment and monitoring are the other issues where, let's say in traditional software development, when a code is written, it is pushed to services like GitHub, GitLab, and then there's some person who's reviewing your code. And before it's getting merged to what is called master branch, it is basically run with these CI tools, which are continuous integration tools. And those tools, they then run like dozens of tests. So they test the heck out of your code. There could be like unit tests, integration tests, end-to-end tests, and maybe even like your code is being deployed before it is productionalized. Some actual person can check it. In machine learning system, these things are way too complicated, and I'll further tell you why they are complicated. So there are some tools that kind of try to help these, to overcome these issues, like Kubeflow, Facet, different stacks that you can use. But again, the underlying issue is always there, and that's something that some people or designer of the system have to take into consideration. So there are also like build SaaS services, which is software as a service, provided by this major player in the game, like Amazon, Google, IBM, Azure. So depending on what kind of approach you use to your model, the complexity of the infrastructure might change, or it might be much simpler. But again, the real world machine learning system, they need continuous maintenance. So you have to kind of monitor and figure out what are the things that are missing, what are the things that need to be fixed. The developing and deploying a machine learning system, as I said, is pretty cheap, but maintaining over time is pretty expensive. So your models and data can actually change over time. So again, depending on what kind of model you are building. So the possible issues that you have to take into account is the data dependency. Data dependency means that, for instance, if a data changes, how it impacts your model, how the model changes, how your training changes, and so forth. Your model complexity changes, for example. That's something you have to take into account. And then, as I said already, reproducibility. Then you need to take care of testing and monitoring. Like once the model is in the production, you constantly have to monitor. You have to have some kind of status check if the model is working, if there are some issues happening. And you have to deal with the changes in the external world, whether it's business related or just model related. So as I said, the boundaries between machine learning systems are not very clear. So, and the system itself is subject to change on 3 axes. The model can change, the data can change, or the code can change. The data could change in terms of its scheme, its sampling or volume. The model could change like in terms of its algorithm, maybe what kind of framework you use, if you have more training, if you do some experimentations, that could change the model. Then your code itself could change. Business needs, bug fixes, configurations, environments, and so forth. So
could I ask one question? Could you go back? Yeah. As some of the audience knows, I like to think about machine learning by 3 components. Does anybody know what 3 components I always talk about?
Could I answer that?
Yes, please.
Yeah, I'm assuming you're referring to hypothesis space, labels, the features, and the cost function.
Yes, so I like to think about machine learning based on 3 components: data, model, or hypothesis space. So hypothesis space is for me more or less the same as the model, and the loss function. Where do I see loss function here on this slide? Where comes the performance measure into play?
Yeah, that's, I guess, a good question.
I see it, but it comes under a different name. What is reflecting here a performance measure, how good a method is?
I'm assuming it's under the model training and experimentations.
Yeah, also, but in the end, what defines the quality of a model? Who is the end customer of a model?
I'm not sure if I'm following.
The business needs. I think the business needs here are the equivalent of the loss function in my view, because the loss function is what allows us to compare different methods. Is one method better than the other? And this depends, of course, on the business needs.
Yeah. All right. So I guess I can continue.
Yes, please.
Yeah. So now we're talking about the machine learning infrastructure. As I said, there's the data pipeline, the machine learning pipeline, and the deployment pipeline. The data pipeline takes care of all the data, how it comes, how it's transformed, how if you have some manipulations, normalization, and all kind of stuff that you have to clear your data. The machine learning pipeline, or this model training pipeline, is a process where you take care of the model, when it's built, what kind of framework is used, and so forth. And the deployment pipeline is, of course, automating some processes, monitoring, status check, and so forth. So, well, this is pretty good graph that shows the workflow of this whole system. So you have this model building, then evaluation experimentation, then you push your model to the production, or maybe you test it before pushing, then you have some deployment. Again, the boundaries in here might be a bit different based on what project you have. Then you have monitoring and observability. Now, as I said, in traditional software development, you can make things like modular approach. Let's say you can build microservices. You can strictly define where are the boundaries for some specific component of the software. You can say that, okay, this thing just only needs some mock data. We can use as some unit test this component, and things should be all right. In machine learning system, things are much more difficult, because in every basically stage, you can tackle different abstraction level, whether it's model, data, or code. So things become much more complicated. And I've already mentioned about some machine learning service, software as a service, that if somebody interested could look into, but they are pretty publicly known. So some pros and cons of ready used solutions. Often the ready-made solution, let's say like SageMaker, Aalto ML, they require minimum amount of work. So you throw your data, maybe you clean it up, and some magic could happen, and your model just predicts some stuff. Many services already have some backups and caching, some real-time status checks, so you don't have to worry about those. And you rarely have to do any kind of maintenance, because some system engineers, they take care of this stuff. Like sometimes if you have some custom package, maybe updating, but that's like pretty small thing to do. But then there are the downsides of this existing solution is that A properly built system is not usually for free. You have to pay for it. Well, in case of a company, that might not be an issue, but in case of, let's say, just some enthusiast, it might be a bit costly. But in case of company, another issue might be the non-disclosure agreement or GDPR compliance requirements. GDPR is General Protection Data Regulation by European Union. It's a law basically that you have to respect and protect users' data. So if you are using custom or if you are using existing solutions, you have to also make sure that there's like this GDPR compliance, and you have to make some NDA with that company or service provider. And often of time, when you use existing solution, they are very hard to customize because they are built for narrow problems. And maybe in some cases that's okay, but over time, when your system changes, then things become a little bit complicated. So machine learning system in practice. This is the second stage of this presentation, and we'll be talking about sales data and forecast before I can actually show you the demo. So the idea here is to build a proof of concept that kind of includes some of the mentioned principles. Of course, covering all the principles is pretty complicated because of time constraint, maybe resources constraint, because this project that I have built, I had pretty limited time to do all the research and build the model. So the basic idea is to extract sales data that goes back to 2015 from some sales source where it's all saved. Then pre-process the raw data, build machine learning model to do some forecast, then present the forecasted data in a measurable matrix, then repeat all the steps every week. So what we need is basically automated machine learning system that has some scheduling. It pulls the data, it runs the code, it builds the model, it trains the model, it validates the model, and then it does predictions, and then it builds the matrices, and everything without basically engineer interaction, just to see how this system could work in practice. So as I said, like this is the workflow, how to implement it. I'll be taking you step by step. This is the raw data in some services. We extract it, we load it, we build the machine learning, we do prediction, and we do some matrices. So extraction. The data of the sales resides in Pipedrive. That's the service that our company uses. That's where the raw data is. And the requirements are periodical data extraction, for example, once a day, once a week, or once a month. Now, if you are using external services, you will need to have some kind of like access to those services, which means that you will need some API token for the requests if you want to build your own system. Then again, external services also require some crash report or status monitor check. So if your request fails, you have to have some places to report it. Then you have to have caching and backup. Like, for example, you pull the data today, but tomorrow you try and your request fails. That means that you have to have this today's data somewhere cached or backed up so that other dependencies on the further on the stages, they do not break. So luckily for me, there was this service which is called stitchdata.com, supports all these requirements, and it also has some integrations with Amazon S3, Pipedrive, and etc. All I needed to do is to check the requirements, check the NDA, and check the GDPR compliance, and I'm good to go. So now I have the sales data in Pipedrive. I have to export it to this with Stitch. Next, I have to build a transform, load, and model implementation. As a matter of fact, our company uses lots of this AWS services. So for me, it was easy to kind of integrate it to Amazon infrastructure. So the data that is exported by Stitch, it goes to AWS 3 buckets. So now I can use Amazon Compute Cloud system, which allows you to create a quite different type of instances or machines run in the cloud, which can get your data and then do some manipulation. So I'm doing the instance in the EC2, transforming the data, doing model training and validation, doing prediction, and putting all the predictions back to the S3 bucket. And why is that needed? Because then further we can extract those predictions with some other tool where we can show matrices. So data processing is done, exporting prediction is done, and because Amazon Export already supports some kind of custom backups, that issue is also done. It also supports scheduling. You can run it once a week. So all these issues at this point are taken care of. Now, the most important question still remains: what type of model to use to build this kind of system? Since we are talking about sales prediction, we are talking about time series data analysis. So if you were to do it properly, you would probably use more robust things like, let's say, in terms of deep learning, you'd probably rely on much more powerful frameworks like maybe XGBoost or something. If you're talking about more statistical approach, then you would probably consider ARIMA or SARIMA to do the analysis and build time series model. But because we want to leverage all these things and we want to automate all the system with a minimum input from the engineer or person, we want to automatize all the system. So in case of SARIMA and ARIMA, the disadvantage is that it does require lots of this kind of human interaction, because you have to know which model, you have to visually see it, you have to do like lots of small tweaks and tricks in order for your model to work. But luckily, Facebook has this open source project, which is called Profit, and it does forecasting at scale. As far as I know, they are using it with their own production based codes. So it kind of like builds a little bit of trust in this model. So it could automatically build the model. You could use it to do like model selection, and you could use it to do forecasting, and it's really fast. And that's probably exactly what we need, instead of like building our own model, doing all the analysis, which is very costly and it requires engineer input. We don't want to do that. We want to automatize all the system. And once the predictions are done, you need to do some visualization. In our company, we use Clipfolio. So for me, it was easy to choose that as a de facto option. And all I needed to do is now to pull the data from AWS in order to build visualization. So Clipfolio supports versatile visualization. It supports scheduling. Again, import once a day, week, or month. It does support caching and backup. It does have some pretty nice interactive dashboard. So in general, this is how the infrastructure will look. A raw data, Stitch exports to S3. S3 builds the model, does the training validation, does the prediction, throws it back to S3 bucket, and from S3 bucket, Clipfolio pulls the data and does matrices. It uses some integrated Plotly, which makes the graphs much more interactive and good. So in every stage, you have backups. In every stage, you have system checkup, status report, and almost in every stage, you have this monitoring. So see, lots of things are already being taken care by ready-made solutions. All I need to do is to kind of like engineer them to orchestrate all the system to work together. If I were to build all the system from the scratch, it would probably take me months. Imagine like building just a status checkup. Like integrating with the tokens and all the stuff. So it's pretty hard work. But because all these services are built, I can just integrate them and implement this whole project in less than a couple of months. So now I can show you how it works in real world. So I have my code here. Now, before I show you, I want you to notice that all the data that you are going to see is simulated. It's not the real Plan Brothers data. Obviously, I cannot publicly show the sales data because it's a company's property. But what I can do is I can simulate basically generate data and then show how the code works. Again, the production version of this code is a little bit different, but I've just built a small Python notebook so that I can just show you how it looks like. I'm using VS Code and some really nice extensions that allow me to run blocks of code as a Jupyter cell so that developing is much faster. I don't have to rely on the Jupyter Notebook's nasty user interface, but just using like your favorite editor, you can just run the cells. So now I'm just importing all the necessary packages. Let's have a look at the data. So we have some IDs, we have some title. Again, all this data is generated. Even the titles are all generated. The names are all fake.
Hold on.
So,
what is this tool?
yep.
This looks amazing.
This is a VS Code, Visual Studio Code. Yes, by Microsoft. And there's also, I'm using like lots of these really nice extensions.
Yeah.
That you can use, one of which is Magic Python. And there is also this Python package, some of the small like extensions that allow all these kind of manipulations.
Okay.
So yeah, as I said, like I personally, coming from software engineering background, I despise Jupyter Notebook, not because how it works, but just because I cannot use all these like fancy shortcuts and the things that I'm used to. So VS Code makes things much easier. You can run your code as if it was just an editor. Then you can just select run cell and it will just run it in the on parallel. So you can just interact with them much faster. So yeah, we have our data now. This is some title, value, the owner who has created the date, some currency, the status, and blah, blah. Now we can clean up. Again, lots of these functions that you see like clean up, they sound magically, but they are actually not. They are just some utilities that I don't want to go into detail because of the time constraints, but all the functions are here. I just import them and I just do them so that the code looks much cleaner, more readable. So now we just clean, for example, removing uppercase letter to smaller and just small cleaning of the data. We can use only the data that we are interested. We can just throw all the title owner. We don't really need it. All we need is the data, the date where the sales happened and what's the value of that per date. Again, there might be like in one day, there might be like several transactions happening. We don't really need that. We just need the accumulative sum for that date to do some productions, forecast for the future. Now, now that we have cleaned the data, we can just save it somewhere. Let's say in data, we can just save it as extended or cleaned or small version. And then we can also check how it looks like. So these are the deals in the size, and this is the time series. So you can see the data is pretty chaotic, so to speak. It's pretty hard to know where is the trend and so forth.
Because
so
it's
now
simulated data, right?
Sorry?
Because it's simulated data. I guess the real data doesn't look like this.
Actually, the real data looks more worse.
Oh.
the simulated data at least have this kind of properties that some dates are not missing and it's kind of like more or less continuous and so forth, but real data looks much worse. So yeah, now the model. So as I said, I'm using the profit from Facebook. I'm using some functions to normalize the data and to split the data into the training and testing using some small tricks and tweaks. We normalize the data so that we don't have these like huge spikes. So now this is the normalized data, and now we can check this is the training data and this is the small test. We just choose a section of it for testing and training. Now, yeah, I have already run that. Now, here we can choose different hyperparameters. And then I have this function called fit and predict. So the fact is that it calculates that there are a total of 150 models. So it will just run different type of hyperparameters just using like typical grid search. It will do the model fitting and prediction, and it will send me the score, mean percentage score. So then based on that, we can check like, okay, which one is the best. And it also shows like some parameters that it's changing based on the Facebook profit. So because I don't want to run it for 150 models, I just limit it to 4. Now we have our model. Now, oops. Okay, guess that was supposed to run. Oh yeah, now we can just take the entire model. We can, the entire data set, we can remove the test data again, because we have the hyperparameters. We can now use the entire data set as a train because we selected our model. Again, the selection of the model just goes on the go. It goes based on the best score value, and the hyperparameters are also passed. So there's minimum interaction from the human being. Again, I plotted all these things so that I can demonstrate how it works. Now I can show you, this is the true value, and this is the predicted. As I said, this data is not the best one, so it's pretty chaotic data, but the prediction seems to be reasonable. I wouldn't say it's the best, but it does kind of hold on some properties of the real data. Now, yeah, I've done that. So now I can see like Facebook profit allows me to see some kind of like components of this. This is the real data. Then I can see the upper and lower bounds, the actual data points. Then there are some trends. You can put their holidays if you have, let's say, things like let's say inflation rate and so forth. You can also put them as a parameters, and it will take care of them, which is pretty nice because I don't want to dig into, let's say, holidays and check every how if the holiday is put, how does the model react and so forth. So it takes care of all this stuff for me. Now then we have the weekly trend, we have the yearly, the daily trend. The daily trend might not be this accurate because I'm just using per day. There's no like timing and so forth. Anyways, now we are done with this model. We can do some predictions. So we have the y-hat, which is our prediction. We have the lower and upper bound and the data, the date for that prediction. Once we are done with the prediction, we can export the data, and we can also check how it looks with the real. We can upscale it now, unnormalized data. So this is the real data, and this is our forecast. The upper bound does seem pretty exaggerated, but let's say the actual y-hat does kind of fall in the same property. Again, this is not the best model, but let's say for the sake of this demo, it works pretty nicely. So now we can see this is our only this part of the forecast. If somebody of the sales guys are interested into checking these things into detail, they have that. I will further show you how I export all this data and so forth. Yeah, I've run that. Now I can check. Now we can check like cumulatively how it changes. It's just the sum of these like upper bound, lower bound, and the y hat. So you can see that, okay, the sales might go up to quite much, very optimistical 16 million, or then it can go to a couple million. Again, all these data are fake, they are generated. Now we can extract the data and we can save the data as predictions. So we are basically done up to this point. Now all I need to do is to show you how the matrix are built. So my model, my service is Clickfolio, it sends API request, it fetches the data, and here's the actual mock data. I have to inform you again and again that this is a fake data, it's not the real data. Now we have this very nice interaction with the model. I can check, let's say I can remove Samuel, Pamela, and some of the people to see how the, let's say, sales data for Dennis Johnson is, which is pretty nice. Or it can show you the entire history of daily sales. Then you have the forecast where you can see the upper bound, the lower bound per day, like November, let's say 26, it's supposed to be 34,000 euros. Then you have this cumulative data and so forth. Then you can also build like different other interaction because you have data which is clean. You can build, let's say, this box plots, which shows you the seasonality, how things are changing per month. Let's say October, you have pretty high variability. You have in June pretty low variability, so you know that where you should put more money in the marketing and so forth. So this is pretty useful tool for sales guys. In here, for example, we have pretty powerful interactive chart. We can also, let's say, change the data, or maybe okay. Can't remember again all these. Oh, here, this might be interesting. We change the data per year. So just like that, we have all the data per year. So in conclusion, I'm sorry if this took a little bit more than what I was expecting, but as a conclusive thoughts, with lots of tools available, it is wrong to think that quick gains from machine learning system or models come from free, because they don't come. They have hidden costs, they have huge technical debts, and the technical debt come in the form of maintenance and keeping them up to date, monitoring them, and so forth. Machine learning systems require an entire infrastructure around them. The actual machine learning code is very small. Everything else around them is called plumbing or DevOps or engineering. So machine learning system, they evolve, the code involves, the model, and the data involves. So when building a machine learning system, it's important to take into account the exploratory data analysis, the discoverable and accessible data, iterative data science flow, as I already demonstrated to you, the model serving, testing, and quality in machine learning, and continuous delivery orchestration, model monitoring, and observations. Thank you very much. That was my research project. Any question?
Thanks a lot for this amazing talk. Are there any questions?
May I ask a question?
Please.
I missed a bit. Is the model fit on this new periodically extracted data and the old data is discarded, or you combine the old data and this new data together to feed the model?
Yeah, that's a good one. So because the data itself is pretty small, it's only from 2015 to now. And from all this period, we have roughly like 400 data points or so, 400 to 500, which is pretty small. And because the model is super fast, I didn't really take into account for the things that I've already built. So I just pull everything from the beginning and then run the model fitting every time. Basically, every time, roughly speaking, you have a new model which is fit.
Okay, thanks.
If that answers your question.
Yeah, sure. Thank you.
Can you show how you kind of pass the data to Prophet library?
Yeah, sure.
To kind of in the code, how do you?
Yep. Yeah. Let's see. One thing I have to notice here, note here is that Prophet is built with the kind of like typical data scientist workflow in mind. So it works really well with data frames, Panda data structure data frames. So if you import your data as a data frame, and you have to basically normalize the data so that it falls into this Facebook Profits requirements. You can read them in their documentation. So all you need to do is, let me find. So here, look, the task data is basically just a data frame. And the requirement is that your value should be called DS. That's all. And the date that you're forecasting, or a single point per date, should be just called date. And because it's a data frame, you have this train and test. Let's say I'm gonna just go here. Wait, where's my training code? Oh, it might be here. I have two models. Yeah, there. So this is a data frame. Model fit and predict takes the data frame, which is here. Like these are all the parameters that you send to model to the Prophet. You initialize it. You can even pass holidays, which you can use some Python package to get the holidays. And the fitting is just the data frame. It's as simple as this. So it's really fast and it's very easy to set up.
And how is this made real time or continuous? So you regularly call this function?
Yes, basically you regularly call it in every time your hyperparameter changes, you call this function and it just fits it and predicts it.
But shouldn't it somehow kind of gradually change the model so it has a current choice for the model parameters, and then it updates the model parameters based on the new data coming in?
Yeah, certainly you. Oh no, sorry. Per every iteration, of course, it doesn't change. So the model fitting, it's a data frame. So it's, let's say it's a vector of 500 data points. You just throw it in and it fits the model and it does the prediction based on that. But of course, what I'm saying is that every time you call this function that it changes in terms of that, like if you are running the training, we send the hyperparameters, and every time we call the function, of course, the model is recreated with the new hyperparameters. But during the iteration, you don't do really the iterations because the data is just a data frame. It's just a data frame with lots of rows, let's say 1,000 rows, and you just pass that into the model fit.
Yeah, Alex, I think they just train this whole data set once a week and they just save that model and you use that.
Yeah.
And even in the next week, if the data comes, for example, they retrain every data set.
Yes.
Whole data set.
Yes.
Once again.
Okay.
But of course, like things like this could be taken into consideration. But as I said, this project is a proof of concept, and I really didn't dig into all these like corner cases where things could be optimized, like you said.
I like to think my background, I studied electrical engineering a long time ago, which is about designing systems, physical systems that optimize the flow of energy or energy in radio waves to get a good coverage for the mobile phones, also flow of information. And I like to think about machine learning systems as systems where information or data flows. So I was thinking that you just need to connect. You need to tell Prophet, here is a URL where you can read in every 2 hours a new chunk of data. And you use this new chunk of data to update your current model. So you don't have to.
Yeah, I'm pretty sure. Yeah, sorry. Yeah.
And there's also
Yeah, go ahead.
in Keras, there's this concept of data flow generators. So I was wondering if this Prophet ties in nicely with such data flow models.
Yeah, I'm personally not very qualified, let's say, Prophet engineer, but this is just like my quick insight into this project. I guess it would make sense to investigate these kind of things in more detail, but I don't actually know like if it supports these type of features or not.
Yeah. Thanks a lot for your talk. It was very nice to see how machine learning is used in practice. So this very practical viewpoint is very good. And I was a bit. I found it a bit curious that you said in the beginning a theory behind practice, or was it theory behind machine learning practice? Well, that's exactly what theory is about. Theory is about developing tools that are used in practice. And a good theory, or one of my favorite quotes is, I think it was by a German a long time ago, there's nothing more practical than a good theory. A theory helps you to avoid going empty miles in machine learning, because you can calculate that you have too little training data for this type of model, for example. Okay, but nevertheless, thanks a lot. So what are the next steps for you? You